Hello everyone, Miss James here. In this video, I want to take on the task of doing some more advanced stuff with your data. So what we have so far done is looked at our, excuse me, we've looked at our data. The lab question was, how does the object distance affect the image height? We have our object distance here, our image heights here. We have our graph down here. HI equals 31 divided by DO. Okay, and in class, we use similar triangles to find that the formula we think should work is HI equals HO times DI over DO. So I want to test how well that works in our data. So I'm going to make a new column called calculated HI. It's also going to be measured in centimeters. And I could plug all these numbers into the calculator and figure it out. Notice that I was a good student and I put these DO and DI in my data table somewhere. These are constants. We kept DO and DI constant. That's not DO. That's HO. Sorry. We kept HO and DI constant. So I'm going to use an Excel formula. The Excel formula says use HO, which is 2.5, times DI, which is 12, and divide it by DO, and I'm going to click here. Okay, the HO and the DI don't change, so I can just put those directly in my formula, but the object distance, I don't want to use the number 3, I just want to use that cell reference. So when I hit equals, shazam, there's the value. I can go to the lower right-hand corner, see how the cursor changes, and pull that down, and I get all these values. And just because I'm a little crazy, I'm going to make sure that it's the right number of decimal places. Okay, now look, 10.2, 10, 5.25. These look pretty close. So in science, you can't just say, hey, these look close. You have to say how close. And the measure of how close is a percent difference. So percent difference. Now, that doesn't have a unit. To calculate percent difference, I take the difference. This minus this, and I divide it by what I expect it to be, which is the calculated. And I do the same thing, go to the lower right-hand corner and pull it down. A couple of things, notice I have to have F4 and E4, the difference in parentheses, otherwise you got order of operations problems. Also notice that I'm getting some negative values, and I really don't care which one's bigger, I just care that they're different. So to get rid of those negative values, you could do ABS, that stands for absolute value of a number, and we're going to revise our formula that way. And then if I pull that down, the numbers go away. Of course, if I made changes to my table, I then need to update the sample calculation. So I need to write out the formula. High equals ho times di over do. High equals ho was 2.5 times 12 over the first line, which was 3, was DO. And then I may want to just double check and make sure everything's going right with my calculator on this first one, but I know it is. So that's 10 centimeters. Okay, and we need to do the same thing for percent difference. So percent difference is measured minus calculated divided by calculated, which means percent difference equals 10.2 minus 10 divided by 10, which equals 2%. All right, so now we have our data table updated. You can futz around with the borders and all that. Oops. Okay. All right, so here we go. The next thing we could potentially do is use a new graphing technique. This is primarily meant for accelerated, but it is a good technique in either case. If we want to show how close our measured values are to our calculated values, we can graph them one against each other. So I'm going to copy those, get out my graphical analysis, get a new graph. I'm not going to save that. I'm going to just put that in here. And of course, I go back to my thing. This first one was measured image height. So HIM in centimeters. Notice it puts it down here. Notice all the points are on the thing. That's so nice. And then this is calculated image height. So it's HIC in meters. Now look at what happens. Notice that the data goes up. When data goes up, it's a line. So I'm going to put a linear fit on this line and make this a little bit bigger so it's easier to see. Now, if what was on the y was completely equal to the thing that was on the x, we would expect the slope to be 1, right? A y equals x line. But look, we've got 0.98, so we're only 2% off of that perfect ideal. To get this graph into your sheet, highlight it and Command-Shift-4 to take a screenshot. Go back into your Excel thing, find a box, insert image. You can't actually, which is kind of annoying, you can't just drag it in there. It won't work. You got to drag it in here. And here's our other graph. We may want to make it a little smaller. Okay, and again, we'd like to write the equation for that line. So we've got what's on the y equals mx plus b. So what's on the y is HIC. That's going to equal the slope, 0.98. And then what's on the x-axis, which is HIM. And the y-intercept is so small, 0.006, I'm just going to ignore it. I'm going to bold that. I'm going to make it larger. Maybe I'm not going to bold it. Okay. You can use this kind of a graph to say how close did your calculations come to matching your measured values. So I hope you guys find this useful and helpful for me to go over this. Have a good day. Bye.